Alright, welcome back. I figured that you guys might like to see some practice problems dealing with force, the stuff for Chapter 4, since all I have so far made for you is the lecture. So online, your textbook actually has some practice quizzes and practice tests and standardized test questions. So I'm going to use those as the questions, and then I'm going to work them out using MS Paint. Alright, here we go. Question number 1. A common symbol for the time interval is delta t. There's nothing to work out there. T final, or T sub f is T final, T sub I is T initial. So delta t means change in time, or the time interval that's elapsed. Question 2. A car is accelerated uniformly from rest up to a rate, or at a rate of 0.5 meters per second squared for 1 times 1. That probably means 1 times 10 to the first, the typo. Its final velocity is 23. What's the initial velocity? So this is actually a Chapter 3 type of question. But we'll go ahead and solve it. It will give you some good practice. So anytime we've got a problem asking about accelerated motion, we know we need to have the 5 values, and they are VI, VF, acceleration, distance, and time. And so I always, as I said in class, recommend you write down the 5 values like this. Then read through the sentence, and then fill in the values you know. So the car is accelerated uniformly at a rate of 0.5 meters per second squared. That means the acceleration is 0.5 meters per second squared. For a time of, we'll treat this as 1 times 10 to the first, so 10 seconds. It doesn't really matter if it's right or wrong. The process is what's important. So the time is 10 seconds. It says it's accelerating uniformly. The final velocity is 23. VF is 23 meters per second. What is the initial velocity? Okay, so that's what we're trying to find. And we don't really need to find the distance. You could if you wanted to, but according to this, they're not asking for it, and we don't have to find it. So we need to find a relationship between VI, VF, A, and T. And of course, you should know that your formula for those is VF equals VI plus AT. And now you can solve this algebraically, of course, and get the VI by itself, or you could plug in numbers first and then solve numerically. I said in class, and I'll reiterate here, I much prefer to solve this algebraically and then plug in. So to get VI by itself, we simply need to subtract AT from both sides, minus AT. So those cancel, leaving us with the formula VI, which we're looking for, equals the final velocity minus the acceleration times the time. So let me scroll down a tiny bit. Actually, that's not so good. We're almost out of space. I can do it here. VF is 23. Minus the acceleration is 0.5, and the time is 10 seconds. So I'll draw an arrow, and then I'll say VI equals, okay, 23 minus half of 10 is 5, so 23 minus 5 is 18 meters per second. Okay, and that should make sense. If you're accelerating at a rate of 0.5 meters per second squared, that means your speed is increasing by 0.5 every second. And if that lasts for 10 seconds, then your speed has increased by a grand total of 5 meters per second squared. So if you ended at 23, you must have started at 18. Very good. Okay, let's scroll down, or do the next one. In the figure, which we don't have, a box has a mass of 6 kilograms. What will the normal force from the table on the box be? So let's just draw a force diagram. For a box sitting on a table. So here's our box. The box is 6 kilograms. Okay, it says the box is sitting on the table. So you can visualize this as, sometimes, even though technically you don't need to draw anything else, it's nice to be like, okay, you got a box sitting on a table. You draw a little sketch. What are the forces on the box? Well, we're trying to find the normal force. The normal force, remember, is the force perpendicular to the surface that prevents it from like smashing through. So if you have a rigid object, you can't push something through it because it provides a force opposing whatever you push onto it. So what force is pulling the box down onto the table? Of course, that's the force of gravity. And we're going to assume that this box is in equilibrium. I don't actually have the picture to look at if there's more information, but assume this box is in equilibrium. If it's in equilibrium, then we know that F net has to equal 0. Okay? Equilibrium means there's no net force on it. It's not moving, it's not accelerating. And so what that means is F net is the sum of all the forces. So you could say the positive force is F normal minus, this is positive because it's going upward. This one is going to be negative because it's going downward. So when you do the sum of the forces, you have to take into consideration their direction. So force normal is up, so positive, minus force of gravity because it's negative, equals 0. And that leads to the logical conclusion that the normal force equals the force of gravity. And I mean, you could probably jump straight to that just looking at it, right? If the upward force and the downward force balance out and they're equal to each other, the net force will be 0. So when there's only two forces involved and something's in equilibrium, it's pretty easy to just say the one up equals the one down, or if it's left and right, the one going to the left equals the one going to the right. But I caution you that when there's 3 or 4 forces all in the same problem, be very, very careful in assigning which ones are equal to which ones. And really do try using this idea that F net equals the sum, including sign, positive or negative, of all the forces in a given direction. Okay, so once we know that the force normal is equal to force of gravity, we can just simply say the force of gravity is equal to mg. We know the mass is 6, and we know g is 9.8. So, oh, I'm out of space, so I'm going to have to go up. See how I use an arrow to show the direction of my workflow? So F normal equals, what's 6 times 9.8? I don't know, 54 plus 4.8, 58.8. 58.8. Sorry, I'm running low on space. I can move over a little bit. And our units are going to be what? This is a force, so our units are newtons. Oh, sorry. I just accidentally jumped up. There we go. Okay, let's go over, make a space. Next problem. Number 4. A motion diagram is a series of images of a moving object that record its position after, this is going to be after equal time intervals. So the motion diagram has them equally spaced. And we said that was kind of like when you use a camera with the, there's a shutter option where you hold the trigger down and it takes a picture every so often. That's equally spaced pictures. And then based on the spacing of the object in the photo or in the motion diagram, you can tell whether it's speeding up or slowing down. And you can tell how fast it's going. If it's going very fast, the dots will be spaced farther apart. If it's going slower, the dots will be closer together because the distance per time interval is going to be smaller. All right, here we go. Do I want to change the color? No. Keep it current. Okay. In the particle model, the what of the object is ignored. Okay. The particle model is where we treat any extended object as a point particle. So we're ignoring any of the characteristics of the object's shape or internal structure. So we're going to ignore the internal motions. But we certainly care about its overall acceleration, its overall position, and then a motion diagram is not a property of the object, but it's what we use to draw the motion of the object. For the situation in a figure that I don't have, F1 equals 200, F2 equals 500, what will F net be? Okay, well let me just make up a picture. So this will be number 6. So here's my object. I don't have a mass, I'm just going to put an m there for the mass of the object. Suppose that I had this, F1 equals 200 newtons, and F2 equals 500 newtons. So I have to use a longer arrow, right? Because 500 is bigger than 200. F2 equals 500 newtons. And they say, what is F net? So again, F net equals the sum, I cannot write, sum of the forces. Sorry, this is tedious. So the sum of the forces, right? But that includes the direction. Because forces are vectors, the direction is really, really important. So you can't just look at this and say, okay, 500 plus 200 is 700. No, 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 because the direction is super important. This 500 is pointing to the left, this 200 is pointing to the right. So we could assign a coordinate direction, and we could say that, let's say that left is negative and right is positive. Okay, then my F net is going to be negative 500 because this guy is pointing left, plus 200 because this guy's pointing right, and we've defined right to be positive, and that's going to equal negative 300 newtons, and then that negative sign tells us it's to the left. I mean, obviously, for something this simple, you can just look at the picture as well, and say the one going to the left is bigger than the one going to the right. So whoever's pulling on the left is going to win, and they're going to win by 300. But again, it's good to kind of see the process, so when they get more complicated and you have many forces all acting on the same object, you're used to it and you don't struggle because you can't do it in your head. Alright, let's do maybe 2 more, and then I'll set you loose on the homework. For number 7, for the situations shown in this figure, if the table has a mass of 35 kilograms and F1 is 20 newtons and F2 is 30, what would be the acceleration? Okay, let's just make up a problem based on that information. So number 7. A table has a mass of 35 kilograms. So here's our table, 35 kg. So we're going to draw a force diagram. So we draw our object with a box around it and put the mass. F1 is 20 newtons. So let's say F1 is, you know what? Let's be pedantic here and say F gravity and F normal, because the table has to be sitting on the ground, right? It doesn't have to be, but probably is. So you've got gravity pulling the table down, and you've got the normal force holding it up. So probably this F1 and this F2 are actually forces that are going side to side. So let's label this F1 equals 20 newtons, and let's label this F2 is 30 newtons. So which way is the box going to go, or the table? The upward force and the downward force are going to balance out, because the table is not rising or sinking into the ground. That's an assumption that we're making. So if you have someone pushing left and someone pushing right, the person over here is pushing harder. So we have here not F net equals 0, but instead F net equals ma, because the table is going to move because the net force is not 0. So what is our F net? We've got a positive 30, and we've got a negative 20. That's because positive 30, I'm assuming, let me just draw this real quick, that this is positive and this is negative. So positive 30 and negative 20, right there, negative 20, has to equal mass times acceleration. What's the mass? 35, and the acceleration is a. So come right over here, and then we can say that the acceleration equals 30 minus 20 is 10, and divide each side by 35. So 10 over 35 meters per second squared. And of course, type that in your calculator or simplify the fraction or whatever you want to do. That would be your acceleration. So it's going to accelerate to the right, and we should maybe even say to the right. The fact that our answer is positive, the fact that the answer came out positive, and I've labeled this little diagram right here, is enough to justify not having to write out it's to the right, but a lot of times it just makes it more clear and it makes your answer more obvious. Okay, so you can again find all of these practice questions on the website. I sent an email actually earlier today with that information, but you can go through more of these, ask me specific questions or email if you have them, but hopefully these examples kind of helped you see what it looks like to draw a force diagram, to set up F net equations, talk about a couple concepts, and good luck on the homework.